Okay, it's 8:20, so I'm going to go ahead and get started. And I have some announcements to make, quite important ones. First, let's just kind of go in order. The next homework set is due this evening. Wiley Plus problems, more practice at the for material at the end of chapter 15. Next Wiley Plus will be due Tuesday evening, just so you can plan ahead. I said everybody could have until Monday to turn in their lab reports, okay, so that you can be working on that with your partner. And I want to talk about how we're going to proceed now for the rest of the semester. The official calendar calls for 2 more days of in-class sessions, Monday and Tuesday of next week, and then the rest of the semester to be remote. I'm going to go ahead and go remote as of Monday. Okay. Class will still happen at the normal times, so we'll have a class Monday morning of next week. And then the week after Thanksgiving, we'll have a class on Monday, Wednesday, and Friday, and Thursday. But they'll all be remote. All you have to do is be at your computer at 8:20 in the morning on a class day and click the Zoom link. I sent everybody the link, the email link, right? You get that. It's an ongoing class. Every Monday, Wednesday, and Friday at 8:20. Okay. And you just go to the Zoom class. And then I will teach the class like I did kind of the review session, for example, on Tuesday evening on Zoom. Okay. And we can still communicate. You can either unmute your audio or type in the chat box during class. But we will have class, but it won't be here. Does that make sense? Things are just getting too much. Okay. Now, what about lab, you may be wondering? I'm going to do a little change to the last experiment. We have one more experiment on transverse waves on a wire, and chapter 16 is all about that. So it's an important experiment. But again, because of all the stuff going on with COVID, and I think the also general fatigue that we're all feeling at the end of the semester, we're not going to meet in session in lab for that last experiment. I am going to provide to you the data that you would take in the lab session next week. And then you will do the analysis and write the lab report. Okay? So I'll be setting up, I'll be uploading that data on Blackboard, probably early next week. And then you do the experiment exactly like the lab manual says, except you don't do the parts where you actually gather the data. We've done that already. And so you will be graded on only those things that you can do, the analysis and the questions. But you would still do a lab report. You still work with your partner to submit one lab report between you and your partner or partners. And you submit it on Blackboard, just like you would any other lab report. And it will be due the end of that last week of classes, which would have been the second week for that experiment. So it follows all the same schedule, except it's remote. Okay? Does everybody understand that? Anybody want to ask a question on that? You can always send me an email if a question comes up later. But I just don't think it's worth 2 more days, especially as I can see what's happening here. I think people are just kind of wearing out. But we still have class and we still have some important content to talk about. Waves, but we'll be doing it on Zoom. Okay? And I'll be recording it and uploading it just like I am here. Okay, so that's what's going to happen for the rest of the semester. So the next time we have class, we go to the Zoom. Okay. All right. Now, in terms of the content, I started with the video lectures for chapter 16 on our Thursday class. And as I often do, if there's a lot to talk about, I break up my video lectures into a couple of parts so that you can take a break more easily, perhaps. So I had 2 video lectures for the introductory material in chapter 16, where we introduced the concept of a transverse wave, transverse mechanical wave on a medium. And we also focused on the specific case of a sinusoidal transverse wave on a medium, in that case, a string, piece of string. And we talked about how we think physically about the wave and the mathematics that we use to describe the wave. So you had 2 video lectures and a class video. So you had 3 videos for Thursday. Hopefully throughout the course of the day, you could find time to fit those in. Certainly didn't have to do it all in one fell swoop. And then you had a video lecture for this morning, where we continue talking about waves. And I had 2 topics. So let me show you the learning objectives. The material is chapter 16, section 3 and section 5. Section 3 was about energy and power of a wave traveling along a string, a sinusoidal wave traveling along a string. And let me just summarize by writing here on the board. Oh, well, that's dead. Let's see if this works. By writing here on the board, the formula for, notice what it says for the learning objective. Calculate the average weight at which energy is transported by a transverse wave. Rate at which energy is transported. That's power. So the formula that we derived is called the average power associated with a sinusoidal traveling wave. It is a little bit of a complicated result, but it's actually important, as I mentioned in one of the video lectures, because waves are so common in nature. The formula starts with a 1/2. That's what you get when you do the averaging of the cosine squared term. Then you need the mass per unit length of the string material. Notice that's a mu, not an m, okay? And that has the SI unit of kilogram per meter. It's mass per unit length of the string that the wave is traveling on, times the speed of the wave, v. That's just how fast the wave is traveling. I don't like that pen either. Let me try this one. Times the angular frequency squared of the wave. That's our old friend angular frequency, which is 2 pi over the period of the wave. Notice it's squared. Then times a symbol we are using now, y max squared. And that y max is the amplitude of the wave. And I emphasized in one of the video lectures how one of the key things that you want to take away from this, the key thing that you'll hear physicists and engineers who are dealing with waves say all the time, is that, oh, the power of the wave goes like the amplitude squared. Because that's the result we got when we calculated the average power associated with the wave. I mean, it depends on these other things. Yes, the mass per unit length of the medium, the speed of the wave on the medium, the angular frequency squared of the wave. But that's the most important aspect of this result, that the average power depends on the amplitude of the wave squared. Okay. Now I want to go on to chapter 16, section 5, because this is perhaps the most important, or one of the most important sections in the chapter, where we introduce the phenomenon known as interference of waves. A quintessential wave phenomenon, interference of 2 or more waves in the same medium at the same time. And so the various learning objectives apply, here's the fancy language, principle of superposition, that means add, okay? Add up 2 overlapping waves algebraically to get a resultant wave, also called a net wave, which I did in the video lecture for today. For 2 transverse waves with the same amplitude and wavelength that travel together, find the displacement equation for the resultant wave and calculate the amplitude in terms of the individual wave amplitude and the phase difference. That one deserves a little more mention. Summarizing from the video lecture for today. All right, now in the video lectures, I introduced this mathematical notation called a wave function. This is a mathematical way to represent a sinusoidal transverse traveling wave on a string. And this formula says I've got a wave I'm going to call wave number 1. And its displacement function y1 of x and t is given by this. Notice sine. It's a sinusoidal transverse traveling wave. And we'll have a second wave function. We'll have a second wave described by a function y2. Its function is going to be the same as the first wave's function in every single way except one. The second wave is going to have a shift relative to the first one. And we represent that mathematically. Notice it's all the same so far as the first wave, but then we add in a phase shift, phi, in the argument of the second wave function. So these two waves that are existing simultaneously on the same string, don't worry about how you would make that happen, are exactly the same in amplitude, in angular frequency, in this symbol. Watch out, that's not a spring constant. It's called the angular wave number. It's 2 pi over the wavelength. They have the same angular wave number. They differ only in that the second wave is got a phase shift compared to the first. Now, if both of those exist on the same string at the same time, then you use the principle of superposition to get the formula for the net wave, because that's what you will observe, the net wave. And the principle of superposition means add. Okay? You add the function for the first wave, the y1 that I've got there, to the function for the second wave, the y2. So I've got to add algebraically these two functions and see what I get. And that's what I do in the video lecture. So I'll let that part stand on its own in terms of how you do that adding. I will just write down what you get, because that's what we're going to use in today's class. When you've done the addition of those two functions algebraically and you've simplified it as much as you can, what do you get? You get 2y max cosine, cosine. I know I only had sines, but now here's a cosine. And inside the cosine is that phase constant phi over 2. And then there's sine. And inside the sine is kx minus omega t. Okay, that at least looks okay, because look what I started with. But then there's a plus, watch out, phi over 2. That's what you get when you algebraically add those two functions. You have to use a trig identity to get there, but that's what you get. And then you need to be able to stand back from that and say, what does that tell me? What is this net wave going to be? All right. First, each of these were examples of sinusoidal, transverse, traveling waves. And there are a couple of ways you know that that's what you've got by looking at this function. First, if it's a traveling wave, somewhere in the function will be the combination kx plus or minus omega t. That's how you know you got a traveling wave. That combination appears. Kx plus or minus omega t. If you've got that combination of the variables x and t, whatever the thing is, it's a wave. It's a traveling wave. We have a trig function here, so we know, and the trig function is a sine, so we know it's a sinusoidal traveling wave. Why is that important? Because we've got to be able to look down here at this result for the net wave and see what kind of wave we're going to get. And because I've got that combination, kx minus omega t, I know I got a traveling wave. Well, that shouldn't be too shocking. I put two traveling waves in, and I get a traveling wave out. Now, it's got a slightly different phase constant than the first two waves, but it's still a traveling wave with the same k and the same omega. But the thing that's new here that we don't have up here is the amplitude of this net wave. We'll call the amplitude of the net wave the absolute value of everything, and I mean everything, that's in front of the sine function. Everything that's in front of the sine function, which in this case is 2y max. These were each a y max amplitude to begin with. I get 2y max cosine of phi over 2. So what that tells me is the amplitude of the wave that I'm actually going to see, that's what you're going to see, depends on what that phase angle there, phi, was between that phase difference between those two waves I started with. And it really all boils down then to what that phi is, because that's going to determine how big of a wave you're going to see. So really, when it comes down to interference, it ultimately boils down to figuring out what that phi is. And from that, you can figure out how big the net wave is going to be. So let's go and get right to some practicing on that. I'll start with a Wiley Plus example that they would call a 1-star problem or 1-dot problem, meaning the simplest level, the most basic, just for practice. Goes like this. What phase difference, okay, that means phi, between two identical traveling waves moving in the same direction along a stretched string results in the combined wave, that's this one, combined wave having an amplitude 1.50 times that of the common amplitude of the two combining waves. They're telling me how big they want this to be. 1.5 times the y max that I started with either one of these waves. So what's the phi? We're to express that answer in radians, because the phi is inside a trig function, so radians, but also is something called a fraction of a cycle. So let me start with that one, because it's not too bad. So interference of waves, part 1. Well, we're told what we want for the amplitude of the net wave. That is to be 1.50 times the amplitude of the individual waves. Y max, 1.50 times Y max. That's what I want. Now the amplitude is given by this formula right here. I put on the absolute value, by the way, on the amplitude expression, just in case I should ever have a situation where the argument of the cosine is greater than pi over 2. Because then the cosine of an argument greater than pi over 2 radians is negative. And I personally don't ever think of amplitude of a wave being a negative quantity. Now, how often will it happen that argument right there is greater than pi over 2? Probably not very often. So most of the time, we won't need to worry about the absolute value symbol. And I'm telling you that in this case, we don't. So here's what I'm saying. Here's the formula that relates the amplitude of the net wave to the phase difference, phi. That's the phase difference between the two waves I started with. So I want that to equal 1.5 times Y max. That's what has to happen. Notice there's a Y max on each side, so they cancel. I don't need to know what the Y max originally was. So let's see. Let's divide both sides by 2. Cosine of phi over 2 equals 1.50 over 2, which is 0.750. Now let's take the inverse cosine of both sides. Phi over 2 equals the inverse cosine of 0.750. Do that on your calculator. Make sure your calculator is in radian mode, please. When you're doing waves and oscillations, put your calculator in radian mode. And to get phi, I have to multiply both sides by 2, don't I? So what I really need to do is that calculation. 2 times the inverse cosine of 0.75 with your calculator in radian mode. And your calculator gives you, to 3 sig figs, 1.44 radians. So that's technically how much wave 2 is shifted. And because that's positive phase shift, that means wave 2 has been shifted to the left of wave 1 by 1.44 radians. The problem, though, and that's perfectly correct answer. The problem is most people don't have any intuition for how big of a shift 1.44 radians is. So a lot of the books will talk about the shift between the 2 waves that are interfering in a lot of other different terms that sometimes get confusing, but ultimately boil down to trying to help us visualize how much these 2 waves are shifted relative to each other. Okay, so yes, they're shifted by a phase difference of 1.44 radians. But they also want it as what they call a fraction of a cycle. What does that mean? All you got to remember is this. For any trig function, specifically sine and cosine, if you add or subtract 2 pi from in the argument inside, the output of the sine or cosine is unaffected. It's periodic with period 2 pi. So 1 cycle is 2 pi radians. So divide the phi that you got by 2 pi radians, technically. So that's 1.44 radians over 2 pi radians. And even though the radian is dimensionless, they still cancel. And 1.44 over 2 pi is 0.23. That means the waves are shifted relative to each other by almost 25% of a cycle, almost a quarter of a cycle. Let me show you with a Wiley Plus animation, which I also showed on the video lecture. Okay, this shows 3 sinusoidal traveling waves. There's wave 1 with my function y1 right there. This is at time 0. This is a snapshot of the wave, and it sure looks like a sine function, doesn't it? Because it is. Wave 2 is this one, whatever the y2 is, but it'd have to input a phi. Well, by default, it chose this number, 1.047. But let's put in what our phase shift is, 1.44 radians, which is probably most easily done by clicking that little down arrow and just typing 1.44. Made a slight effect there. Okay, there is y2, the sinusoidal wave with the phase shift or phase constant phi of 1.44 radians. And I recommend you think of this one as being simply this one shifted to the left a little bit. How much? Well, technically 1.44 radians, but here's another way to think of it. Look at the first one. This is y1 in centimeters versus x in meters at the time t equals 0. I can see from there to there is 1 complete cycle. So that distance is the wavelength of the wave, symbol lambda. Looks like the wavelength is 1 meter. How far? So that's what I mean by 1 cycle, 1 wavelength. Okay. How far has this one been shifted to the left? Well, see where the peak was here? How much is, follow that one, it's this one. How much has it been shifted to the left? Almost 0.25 meters. In fact, 0.23. So 0.23 of 1 cycle. This one's been shifted to the left. The bottom curve is the net. This is what you would actually see on the string. You wouldn't see those, you'd see that. And remember, the whole point was to get a net wave with an amplitude of 1.5 times the amplitude of the original waves. Note these original waves have an amplitude of 1 centimeter. So this one should have an amplitude of 1.5 centimeters. And if you look, there's 1 and there's 2, and it goes right up halfway between 1 and 2. Okay? Okay, so the point is, we want to get used to the idea of taking two sinusoidal waves with a phase shift between them and figuring out how big the amplitude of the wave I'm going to get out is. And we talked in the video lecture about two extreme amplitudes down here, the biggest and the smallest that you can get. The biggest possible amplitude you can get is when the cosine term is 1, that's 2y max. And that happens when, well, when the cosine equals 1, which is when the argument phi over 2 is 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. Now that's phi over 2. So that means phi would be 0, plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi. So if the phase difference is 0 or an even integer multiple of pi, I'll get the biggest possible amplitude. That's called fully constructive interference. And it'll be 2 times the original amplitude. So I just put that in here. I'll put in 0. That's the easiest one to put in. Notice they're now exactly in phase. They're exactly lined up. And look at the amplitude of the resultant. Twice the amplitudes of the original. Fully constructive. Biggest amplitude you can get. But the smallest amplitude you can get is 0. When the cosine of phi over 2 equals 0. Well, cosine equals 0 when its argument is plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. But that's phi over 2, so multiply by 2. So that's plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, plus or minus 7 pi. So if you have an odd integer times pi, this will vanish, the whole amplitude will vanish. You'll have no amplitude at all. That's called fully destructive interference. The way I do that on this animation is I drag this slider for phi to the far right. Notice it's 3.142, that's basically pi. Notice that these two are now exactly out of phase. Exactly. Crest lines up with trough. And look at the net. Nothing. Okay? And you can use that phenomenon in technical applications too. Right? You ever hear of noise canceling headphones? That's what they do. They sample the ambient noise, they produce noise that is exactly out of phase with that, and that cancels most of it out through fully destructive interference. Okay, so it's a very important phenomenon. So I want to do one more Wiley plus problem that is a little more challenging, but still boils down to how to express how much my two sinusoidal waves are shifted relative to each other. Okay. All right, I'm going to have to get myself some board space here. And then we'll tackle this slightly harder example involving interference. Let's call this one, this example, interference of waves, part 2. Let's call it that. Here's the scenario. We have two sinusoidal waves. Note that number, 120 hertz. Watch that unit. If they tell you the number in hertz, they're telling you what's called the frequency of the wave. How many cycles per second it completes. 120 hertz is 120 cycles per second. F. Same frequency, same amplitude. They're to be sent in the positive direction of an x-axis that is directed along a cord under tension, which is exactly the scenario we've been talking about. The waves can be sent in phase or they can be phase shifted. Imagine doing different experiments where you change how much the phase shift is between the two waves in each experiment. But they always have the same frequency, F. Therefore, the same angular frequency omega, remember omega, the angular frequency is 2 pi times f. So they have the same f and omega. They're traveling on the same chord in the same direction, plus x, and they have the same amplitude. That's exactly the scenario I was just talking about. Exactly. So all that physics that we were just talking about is going to be applicable here. Now, we've got a graph, as we so often do in our homework problems. This graph plots what they call the amplitude, and they use the notation y prime. If you're used to a prime meaning a derivative, it doesn't mean a derivative. That's just this author's notation for the amplitude. And what they really mean by amplitude is this part of our net wave, okay? In other words, what I called the amplitude, but without the absolute value symbol. That's why he's got going into negative territory over here. That's the way they chose to do it. Okay, so what is plotted? The amplitude of the net wave, but versus what? The distance of the shift between the waves. How far one wave is shifted from the other. It's denoted shift distance delta L in centimeters. The scale of the vertical axis is set such that this number, what they call ys prime, is 6 millimeters. 6 millimeters there, okay? All right. If the equations for the two waves are of this form, y1 of x and t is y max sine of kx plus or minus omega t, it's not both, it's one or the other. We're going to have to figure out which. y2, y max sine of kx plus or minus omega t plus phi, the phase shift. But that's in radians. So we are to find the amplitude of those waves, y max, the angular wave number k, the k that you see in the formulas there, the angular frequency omega that you see in the formulas there, and the correct choice of sign in front of the omega. It's not both plus and minus, it's or, plus or minus. You got to figure out which it is. All right, so here's my point. There are multiple ways to speak about, to express the shift between two waves. I want to list them because you're going to find these different ways in all the books. You can just talk about a phase shift phi in radians. You can talk about a shift as a fraction of a cycle. That means take the phase shift in radians and divide it by 2 pi, like I just did in that first example. You can talk about the shift as an actual distance that I'll denote delta L. So that's got to have dimensions of length, like meters or centimeters or something like that, not radians, okay? Distance is that operative word. Shift as a distance, delta L, or shift as a fraction of a wavelength of the wave, which means take the shift distance delta L and divide it by the wavelength, because those both have dimensions of length. So that's dimensionless, just like that's dimensionless. Those are some of the ways you'll come across expressions for how much two waves are shifted relative to each other. And I still want to talk about this concept. So let me do a little aside here. Okay, I want to draw some pictures, and I want to have this in front of me because I want to draw these pictures as carefully as I can. Let's take the first wave, y1, to be, let's give it an amplitude of 1. And I'll just write it as kx, because I'm going to talk about, I'm going to plot it for you, and I'm going to plot it at t equals 0. And I'm going to give this one a phase constant of 0. So in other words, let's just make a sketch of y and versus x. And I put the x units in, well, it really doesn't matter, but I'll do centimeters since this problem does centimeters. 1, 2, 3, 4. Just to give some numbers. But it's a sine. So sine starts here. I'm going to draw it like this, so that I fit exactly one wavelength over that distance. I chose that, okay? Note that's one wavelength of the wave, one cycle, okay? That's one wavelength, lambda, from there to there. Now let me take the second function. I'll write it over here. Same amplitude, same k, but let's give it a phase shift, phi, of pi over 2 radians. Okay, notice that's a phi. Now let me sketch it. This is y1. This will be y2. X in centimeters, 1. I got to try to line this up. This is where I said I was trying to get this drawn carefully. So this is a wave. I'm sketching it at time 0, but it has a phase angle of pi over 2. Here, we benefit from all of our trig knowledge, because you can use what we know about the sine of two things added to simplify this. Sine of the first, cosine of the second, plus cosine of the first times the sine of the second. And you discover that that simplifies to simply cosine kx. It's still the sine curve, but with a phase shift of pi over 2 radians. But that means it's a cosine. So now let me try to draw that, but I got to try to get these lined up. 1 to 1, 2 to 2, 3 to 3, 4 to 4. And of course, the cosine starts at a maximum when x is 0. And it's got the same wavelength as this one, same k. So it's going to be going down like that, and then through a minimum, and then through 0, and then up like that. That's part of the cosine. I am to think of that curve as that one that's been shifted. How much has it been shifted and which way? It's been shifted to the left, and follow that point right there, the peak on that one. It has now appeared there. So the distance that they have been shifted between each other, the shift distance, is that right there. That's the delta L this problem is talking about, at least in this example. Okay? So here's my point. Lower curve, this one, equals upper curve shifted left by a distance, delta L. It's a distance this way because that's in centimeters. How far? Well, it's clearly 1 centimeter, but the more important way to write that here is to note that that distance of 1 centimeter is 1/4 of the wavelength. So I'm going to write that as lambda over 4. That's for this particular phase angle, pi over 2. So delta L over lambda, 1/4. You can certainly write it that way. I just divided both sides of this by lambda. But now, let me remind you, so that's an important point. I'll put a bullet by it. Let me remind you what the phase difference between the waves is. Phi equals pi over 2 radians. Remember, I started with that. Let me take that form, that expression, and divide both sides by 2 pi. Why not? Then look what's left on this other side. 1/4. Note, phi over 2 pi for this wave is 1/4. Delta L over lambda, shift distance over wavelength, is also 1/4. So what I've got now is, let me get myself some board space, a very useful general result. The phase shift phi between two waves divided by 2 pi is equal to the phase shift distance, delta L, divided by the wavelength. This is a very handy result when you're studying interference of waves, and will show up in a lot of different wave scenarios. And that's what I'm going to use. So please don't file that away thinking, well, that was the one he used for that particular example problem. That relationship is used all the time, which is why I wanted you to see it. Now, I've done a lot of the work on this problem in the front. I front-loaded most of the work, wanting us to understand these ideas. But the little squiggle there means that's the end of the aside. Okay, there's the end of the aside. Because now I'm going to use this idea right here to finish off this problem. So again, to remind you, I, in part A of this problem, have two waves. That one for wave 1, that one for wave 2. Only differ in the phase shift. I know the net wave that I get by adding them will be 2y max cosine of phi over 2 sine of kx plus or minus omega t plus phi over 2. And what they're calling the amplitude of the net wave is this part. 2y max cosine phi over 2. This part. Everything multiplying the sine. All right. Now, how am I going to bring that graph into the problem? Obviously, we have to use it. Whenever you have a problem with the graph, as I've said before, you need to, using correct physics that is pertinent to the section, derive the formula for the thing that was graphed. Okay? We need to derive the formula for the amplitude of the net wave versus delta L. I'm almost there right here, because that's the amplitude of the net wave versus phi. Aha, but that expression that I just marked relates phi and delta L. So we're just going to substitute that phi over 2, the phase shift between the waves in radians divided by 2 is, just multiply both sides of this by pi. Pi delta L over lambda. And so my amplitude of the net wave is 2y max cosine of pi times delta L over lambda. That's what they graphed. Amplitude as a function of delta L. Okay, that's what they graphed. And now all we have to do is take some points off the graph to learn important values. Let me bring the graph back so we can see it again. Okay, that's their notation in millimeters, but that's our amplitude versus delta L in centimeters. Doesn't that look like part of a cosine? It is. I like to take simple numbers off a graph when I have a problem with a graph. Like put the quantity on the horizontal axis value at 0. That's pretty simple, and see what you get. So if we put delta L as 0, no phase shift at all, I get the biggest possible amplitude. Well, that makes sense. And it's up there, which would be 6 millimeters. So let's start with that point. Okay. So when delta L equals 0, the amplitude is 6 millimeters. That's from the graph. But there's the amplitude formula. Let's see what we get from that. So from the formula, 2y max cosine of 0, right? I plugged in delta L equals 0. Cosine of 0 is 1. So the amplitude is 2y max because it's fully constructive interference there. So all I do is combine these two because they both have to be the same. So 2y max equals 6 millimeters. So I know the amplitude of the individual waves. That isn't one of the things they asked for, so I won't underline it. At least, actually, that is, I think, one of the things they asked for. So there it is, 3 millimeters. That's the amplitude of the individual waves. They were each 3 millimeters, and when I combined them at fully constructive interference, I got 6 millimeters. Now let's take one more point off the graph. How about the other kind of clear special point, where the amplitude crosses through the value 0? No amplitude at all for the net wave, right? That's what that means. No amplitude at all. That must mean fully destructive interference. And that happens at a delta L of 10 centimeters. So let's use that fact now. That's the only other point we'll need. When delta L equals 10 centimeters, the amplitude equals 0. That's straight from the graph. Now let's see what we can learn about what goes with that from the formula for the amplitude. How do I get a 0 here for this, right? I got to get a 0 for this amplitude. It's got to come from the cosine. Neither of those two pieces is 0. It's got to be because the cosine equals 0. Cosine of pi delta L over lambda must equal 0. You got to know your trig. Cosine of blob equals 0. What does that tell you about the blob? Take the first value such that the cosine of it is 0. Pi over 2. Cosine of pi over 2 equals 0. So that blob inside there must be equal to pi over 2. Divide out the pi. And what I can get from this, because I already know the delta L, right? It's 10 centimeters, is the wavelength of the waves. Okay, that's something important that they didn't tell me. And it looks like the wavelength is 2 delta L, which is 20 centimeters. Now I know the wavelength of the waves. What do I learn from that? Well, part A asked for, get the wording here. It asked for the amplitude, so we did that. Now I'm ready to do part B, because part B asks me for the angular wave number, K, of the two waves that I combined. K equals 2 pi over the wavelength. You want to remember that. Now I can use that wavelength. 2 pi radians. Watch out, convert that wavelength to meters. 0.2 meters downstairs. When I do that, I get 31.4 radian per meter. Yes, those are the units of angular wave number. The other parts are quick. Part C asks, what's the angular frequency of the waves that were combined? Just use that right there. 2 pi f. And there's the f. So 2 pi times 120 hertz. The 2 pi has a radian with it, and the hertz is really just 1/2. So this is units of radians per second. And to 3 sig figs, it's 754. So 754 radians per second. And D. What's the correct choice of sign in front of the omega? The waves that were given to me were y max sine of kx plus or minus omega t, and y max sine of kx plus or minus omega t plus phi. Which is it, plus or minus? It's not both, it's an or. The thing you got to remember is, if the wave is traveling in the plus x direction, then the argument is kx minus omega t. If the wave is traveling in the negative x direction, then the argument is kx plus omega t. Note, those signs might seem wrong. They are not. We were told that our waves were traveling in the plus x direction. So the correct sign in front of the omega is the negative. Okay. So what's going to happen now, as far as what we're going to be looking at? So we have one more class on chapter 16. That'll be our Monday class. Remember, that'll be on Zoom. And we're going to continue to talk about interference of sinusoidal traveling waves, but we're going to come up with a slightly different scenario than here. So there's one more topic of interference to talk about in chapter 16. And it is, in fact, that topic that is the subject of the last experiment in lab. Then, the week after Thanksgiving, which is the final week of classes, all remote, everybody will be home and comfortable, hopefully. We have chapter 17, where we talk about another chapter on waves. And there we'll talk about longitudinal waves, and we'll focus on the most common form of longitudinal wave, which is a sound wave. Okay. I am working on grading the midterm. I'm well over the halfway mark. So certainly by Monday morning, I will have those graded and uploaded to Blackboard. Okay. Otherwise, you got Wiley Plus to work on, and don't forget you got your experiment 7 lab report to work on. But no quiz today, homework tonight, but no quiz. Okay. In fact, there won't be any more quizzes probably. All right. Okay. Have a good weekend. Try to get some rest.